Hey everyone, I'm just gonna wait a few minutes for people to join the stream. We only have like 30 something people right now, so I'm just gonna wait a little bit more to hopefully get more people. How many people are in the Zoom? 45. I told them the stream's up. Okay, I'm just gonna go ahead and get started because we're gonna start with a little bit of a review. So today we're gonna be talking about limiting and excess reactants. So just as a review of, can you check on the homework for tonight? Just as a review of chemical reactions, like we talked about yesterday. So we write chemical reactions as reactants with an arrow going to products. And then stoichiometric coefficients, which we get by balancing our reaction, tells us the ratio of the different molecules. So if we have like 2A plus B goes to C, I don't think we've shown you a reaction that looks like this before. So you'll see this a lot, especially in engineering classes. Basically, A, B, and C represent some kind of molecule, like H2O or CO2 or whatever, and we have just sort of been too lazy to actually write out all of the atoms that are part of those molecules. So we just write A, B, and C as representing some kind of molecule. There are bonds in there and we just don't worry about it. So this is honestly just a shortcut. Like if you had a really complicated reaction like C6H12OH or whatever is your molecule and you just like don't want to keep writing that out a bunch of times, we might just substitute A or X or something for it. So just so you get used to seeing that. There will be a couple examples like that today. But so stoichiometric coefficients tell us the ratio of the different molecules in this reaction. So what these stoichiometric coefficients here mean is that 2 molecules of A plus 1 molecule of B react together to give 1 molecule of C. So if I want to make 1 molecule of C, I need 2 molecules of A and 1 molecule of B. And then moles are a count of the number of molecules. So 1 mole is 6.022 times 10 to the 23rd molecules. So I think of moles just as like a number. So just like, thousands, you can think of as a unit of number almost. If I can say if I had 2,000 molecules of A and 1,000 molecules of B, that would give 1,000 molecules of C. So the same thing applies to moles. So 2 moles of A plus 1 mole of B gives 1 mole of C. So molecules and moles exist in the same ratio because it's just a conversion factor that's the same no matter what our molecule is. However, mass does not fall into this ratio. So if I had 2 grams of A and 1 gram of B, that doesn't mean I get 1 gram of C, because the molar mass of A and B and C might be different from each other. So those stoichiometric coefficients only give us ratios in units of moles or molecules, but not in units of mass. Okay, I'm going to pause here in case there are any questions, because it's really important that you understand what stoichiometric coefficients mean and the difference between moles and mass, or you'll be really confused for the rest of the lecture today. So I'm going to pause for any questions. Please put any questions in the chat if you have them. And then just remember to convert between moles and mass, you can use the molar mass. So if I have H2O, I can look on the periodic table. The mass of hydrogen is 1 and oxygen is 16. So the molar mass of H2O is 16 plus 1 is 18. So H2O has a molar mass of 18 grams per mole, and we can use that to convert between grams and moles. Okay, just going to wait a little bit more if there are any questions. Okay, I'm going to keep going, but as always, please put questions in the chat whenever you think of them. Okay, so we've talked a little bit about conserved quantities. It came up on the one of the homeworks recently. So I want to talk about conserved quantities specifically with regard to reactions. So I'm showing a reaction here that's H2 plus O2 going to H2O. And I want to point out that I've already balanced this reaction. So I can check, and on the reactant side, I have 4 hydrogen atoms and 2 oxygen atoms. And on the product side, I also have 4 hydrogen atoms, 2 each in each H2O molecule, and 2 oxygen atoms, 1 each in each H2O molecule. So I want you to talk in your groups about whether you think the following quantities will be conserved as I run this reaction. So mass, that is if I start out with 100 grams of total reactants and run this reaction for a while, will I still have a total of 100 grams of stuff? Number of atoms of each element, number of atoms period, and then total moles of molecules of any kind. So I'm just going to pause for a while for you to discuss this in your breakout rooms. Make sure you've accepted those invitations. Okay, I'll just give you about 20-30 more seconds. Okay, so let's come back together. Okay, so mass is going to be conserved for sure. So however much mass we start out with, at any point along this process of running our reaction, that must be our total mass. So if we have gotten halfway through and we've used up half of our reactants and made half of our products, then we'll still have a total of 100 grams of total stuff. So mass is conserved. Atoms of each element, yes, so that's what we relied on in order to balance our reaction. So I have 4 atoms of H and 2 atoms of O on each side. So no matter how far along I am in the process of running my reaction, I'll always have the same number of hydrogen and oxygen atoms. Another explanation for that is that we're not doing any nuclear reactions, so there's nowhere for an atom of oxygen to go or a way for it to appear out of nowhere. So all that's happening is bonds and electrons are being rearranged, but my identity of my atoms is not changing. And so that means that if the number of atoms of each individual element is not changing, then the total number of atoms also can't change. However, moles are not conserved. So moles are a count of the number of molecules we have. And so right now we have 3 moles on the left, so 2 moles of H2 and 1 mole of O2, and we're making only 2 total moles, 2 moles of H2O. So moles are not conserved. So if I start out with 100 grams of stuff, I have to finish with 100 grams of stuff. But if I start out with 100 moles of stuff, I don't have to finish with 100 moles of total stuff. So that's just something to keep in mind. Another quantity that's not conserved, that's a little less related to reactions, is work. That came up on one of your recent homeworks. So if you have questions about that, look at the solution guide, and you can also ask us after class. Okay, so these are sort of the important conserved quantities and not conserved quantities for reactions. So now I want to give an example of how we can use this information, in particular the stoichiometric coefficients, to actually do math with real reactions. So this is the same reaction I had on the previous slide. So I have 2H2 plus O2 going to 2H2O. And if you just remember, we never do anything with unbalanced reactions. So if you're given a reaction on a test and asked to solve for anything, like even before you get to part A of the question, insert a part for yourself, which is this reaction balanced? And if not, balance it. It's never a bad idea. It will never hurt you in any way. So like I said earlier, stoichiometric coefficients tell us the ratio of different molecules, which we can give in units of moles in a reaction. So a really common question that I might ask is, if I want to produce 6 moles of H2O, how many moles of H2 do I need, and how many moles of O2 do I need? So you might be able to just intuitively be like, well, you know, the stoichiometric coefficient of H2O and H2 is the same, so I probably need the same number of moles of H2 as I want to make of H2O. But I just want to write that out a little more formally. So I'm using these stoichiometric coefficients like a unit conversion. So if I have my 6 moles of H2O and I multiply it by the ratio of those stoichiometric coefficients, then I can get my answer in units of moles of H2. And we talked about this on day 2, I think. But just like you can cancel out things in sort of normal fractions, you can cancel out units here. So I have 6 moles of H2O, and then I've put units of moles of H2O on the bottom of my conversion factor so that I can cancel those two out and get my final answer in units of moles of H2. So I can do exactly the same thing with O2, except now I'm using different stoichiometric coefficients to get my final answer in units of moles of O2. So I have 6 moles of H2O, and then I know that I use up 1 mole of O2 for every 2 moles of H2O that I make. So that means that I need to use up 3 moles of O2. Okay. Put any questions in the chat if you have them, because we're going to move on to mass in a second. Okay, if anyone adds any questions, I'll answer them when I get to the end of this slide. Now, a related question that seems really similar is, I want to produce 36 grams of H2O. How many grams of H2 do I need, and how many grams of O2 do I need? Our first instinct might be to say that sort of the same ratios that we used in the first part of this problem apply here. That's wrong. We have to convert to moles. If we didn't convert to moles, we would say, okay, I need the same number for H2 that I need for H2O, so therefore I need 36 grams, and I need half that for O2, so I need 18 grams. There are a lot of problems with this, but one check that you can do is that mass needs to be conserved. So I'm starting out with 36 plus 18 grams, and I'm ending up with 36 grams. So some mass, some 18 grams, is just disappearing, going from reactants to products. So this can't work. And the reason it doesn't work is that those stoichiometric coefficients are giving us a ratio only in units of moles. So I'm going to go through how to solve this one kind of in one step pretty quickly. But if that's confusing, on the next slide, I'm going to break it down into a lot more steps. So don't panic. So what we need to do is we need to take our 36 grams of H2O. We need to convert it to moles using its molar mass. So there's 1 mole of H2O is 18 grams of H2O. Now I can use my conversion factor to go from moles of H2O to moles of H2. So that's my stoichiometric ratio. And then I can use the molar mass of H2 to convert moles of H2 into grams of H2. So I can do a check and be like, my units of grams of H2 both cancel out with each other, moles of H2O cancel out with each other because I have one on top and one on bottom, moles of H2 cancel out with each other because I have one on top and one on bottom, and I end up with units of grams of H2. And then I can do totally exactly the same thing with O2. So I'm converting my grams of H2O to moles, and then I'm using my stoichiometric coefficients to get into moles of O2, and then I'm converting from moles of O2 to grams of O2, and I end up with 32 grams of O2. And now, just as my check, I can confirm that mass is conserved. So I start out with 32 grams of O2 and 4 grams of H2. That's 36 grams total. And I wind up with 36 grams of H2O. So I started out with 36 and ended up with 36 grams. Thumbs up, this works. That's always a good check to do at the end. If you ever do anything and find out that mass is not conserved, something has gone wrong. So on the next slide, I'm going to go through an example of a little bit of a more complicated problem and kind of breaking it down into more steps. So if I have this reaction that's solid aluminum plus chlorine gas goes to AlCl3, so aluminum chloride. let's say that I have 535 grams of Cl2, and I have an infinite amount of aluminum. So no matter what I do, I'm not going to run out of aluminum. So if I run out of anything, I'm going to run out of chlorine. And I want to know how many grams of AlCl3 will I be able to make. So step one, always convert, balance my reaction. So if I do that, I'm going to get 2 aluminum plus 3 Cl2 goes to 2 AlCl3. So hopefully you all are pretty comfortable with balancing reactions after yesterday and after problem set 6. But basically what I did is I started with chlorine, and I noticed that there are 2 chlorine atoms on the reactant side and 3 on the product side. So my least common multiple is 6, and so I knew that I needed 6 chlorines on each side. So I put a 2 and a 3 there. And then I put a 2 in front of my aluminum just to balance my aluminum atoms. So now I have 2 aluminums and 6 chlorines on each side. Okay, so now I know I need to use my stoichiometric coefficients, and so that means that I need to convert to moles. So I'm going to take my chlorine and I'm going to convert it to moles. So I looked on the periodic table. The atomic mass of one atom of chlorine is 35.45. So Cl2 has 2 chlorine atoms, so its molar mass is 70.9 grams per mole. And then I can convert my 535 grams of chlorine into moles using that conversion factor. So I have 535 grams of chlorine, which is equivalent to saying I have 7.55 moles of chlorine to start out with. Then I can use my stoichiometric coefficients, and I know that for every 2 moles of AlCl3 that I make, I use up 3 moles of Cl2. So I got those numbers off of my balanced reaction. Those are my stoichiometric coefficients. And when I just do that math, I can make 5.03 moles of AlCl3. And then I can pretty easily just convert back to mass. So using the molar mass of AlCl3, I have 5.03 moles times 133.34 grams per mole. So that means that I could make 671 grams of AlCl3 if I had 535 grams of Cl2. I'm gonna make you all do a practice that's exactly like this, but with slight difference in a second. So I'm gonna pause if anyone has any questions about how I did this or like why I did any of the things that I did. Go ahead and put that in the YouTube chat. And please don't be shy. If you have any questions, please tell us. Oh, can you explain step 3? So in step 3, I'm using my stoichiometric coefficients as like a ratio of how many moles of different species I need. So what my stoichiometric coefficients mean is that whenever I use up 2 moles of aluminum and 3 moles of chlorine, I make 2 moles of AlCl3. So if I want to make 2 moles of AlCl3, that means I need to use up 3 moles of Cl2. So what I'm trying to find here is if I use up 7.55 moles of Cl2, how many moles of AlCl3 can I make? And so I know that for every 3 moles of Cl2 that I use up, I make 2 moles of AlCl3. So I'm using those stoichiometric coefficients of 2 and 3 as a ratio to convert basically from moles of Cl2 to moles of AlCl3. Okay, I'm gonna put up a practice problem for you all. So let me know if you have questions as your group is trying to solve this. So I have the exact same reaction, but now I'm saying I have 255 grams of aluminum and an infinite amount of Cl2. How many grams of AlCl3 can I make? And I'm giving you the molar masses here just so you don't have to look them up. So make sure you do know how to find those using a periodic table, but for this problem, I skipped that step for you. So basically what I'm asking is, I'm never going to run out of Cl2. I have an infinite amount. But at the point that I run out of aluminum, how many grams of AlCl3 will I have made? So I'm going to give you a little while to work on this in your groups just because there's a decent amount of math on this one. Yeah. And then as we go, I'll kind of pop up the steps. Yeah. Does like 2 more minutes seem like enough time? Just let me know in the chat if your group is totally done, if you're totally lost, if you feel like you need a lot more time. Cool. Someone said they need about 1 to 2 more minutes, so we'll stop in about 1 to 2 more minutes. Sounds good. Okay, in about 10 seconds, let's come back together and I'll start going through the solution. Okay, so the first step is always to balance our reaction. I know I sound like a broken record, but seriously, never do anything without balancing your reactions. It's a very easy way to get a problem very wrong after doing a ton of work, because that's sort of usually the easiest step. So we have 255 grams of aluminum, so we need to convert that to moles. So 255 grams of aluminum, where 1 mole of aluminum weighs 26.98 grams, that means we have 9.45 moles of aluminum. Now we can convert those moles of aluminum to moles of AlCl3. So in this case, both of our stoichiometric coefficients are 2. So for every 2 moles of aluminum that we use up, we make 2 moles of AlCl3. So that means that we can make, from 9.45 moles of aluminum, we can make 9.45 moles of AlCl3. So then the last thing we need to do is convert those moles of AlCl3 back into mass. So we take 9.45 moles of AlCl3, then we use the molar mass of AlCl3, so we have 13.34 grams per mole, and that means that we can make 1,260 grams of AlCl3. So hopefully that makes sense to everyone. I'm going to wait just a little bit for questions in case some groups got a totally different answer or got confused. Okay, so the next thing I want to define for you is called limiting reactant. So the definition of the limiting reactant is basically which reactant will run out first. So if I have this reaction 2A plus B, okay, so there's a question on the previous slide about like what we're trying to do here. So honestly, I think what I'm about to do is going to answer that. But basically, we want to know if I had, 255 grams of aluminum, what is the amount of product that I can make? So that is super relevant if you're trying to like run reactions like in your lab or in a factory. You want to make product and you need to know how much reactant you need, Or similarly, if you have this much reactant, you want to know how much product you can make. So the part about it is often true that if, say, one of your reactants is oxygen and you're doing this reaction in air, you have a functionally infinite amount of oxygen, so you have a different reactant that is limiting. So I will show you on the next slide kind of why we need to do these calculations. So my limiting reactant is the reactant that will run out first. So if I have a reaction that says 2A plus B goes to C, and let's say that I have 5 moles of A and 2 moles of B, I want to know what my limiting reactant is. So if I have, I'm just drawing it out visually here, if I have 5 moles of A and 2 moles of B, and this is the reaction that I'm running 2A plus B goes to C, I want to know which reactant will run out first. So let's just go through it. If I make 1 mole of C, I use up 2 moles of A and 1 mole of B in order to do that. If I make another mole of C, I use up 2 more moles of A and 1 more mole of B. And now I'm totally out of B. So even though I have A left over, I'm out of B. So B is my limiting reactant. It's the thing that is going to run out first. And then A, I have A left over, so A is an excess reactant. So this might answer the question in the chat of why should I care about sort of the answers to these questions is when we combine what we did on the previous slides, we can figure out which reactant is limiting. And we really care which reactant is limiting because if we want to make more product, that's the reactant we need to add more of. And then just sort of another terminology thing, if it's ever the case that A and B would run out together, they are in a stoichiometric ratio. So in this case, I would have an A to B ratio of 2 to 1 in units of moles. So for example, if I had 4 moles of A and 2 moles of B, they're in a 2 to 1 ratio and will run out at the same time. So in that case, neither of them is the limiting reactant. And then just one more point of confusion. If all I've given you is 2A plus B goes to C, you don't know what the limiting reactant is. You need to know how much of each you actually have in front of you, and then use the stoichiometric coefficients. So just as an example, if I go back to those calculations that I had you do a couple slides ago, I have this reaction where 2 aluminum plus 3 chlorine gas goes to 2 AlCl3. And let's say that I have 535 grams of Cl2 and 255 grams of aluminum. I want to know which of these is limiting. So I'll just remind you the answers that we found on the previous slide. So what we found was that if I had 535 grams of chlorine and an infinite amount of aluminum, I found that I could make 671 grams of AlCl3. And with 255 grams of aluminum and an infinite amount of chlorine, I found that I could make 1,260 grams of AlCl3. So I want you to talk in your groups for a second about which reactant you think is limiting. And to the person in the chat who asked intuitively what these questions are asking, let me know if this didn't explain that and if you have a different question. Okay, let's come back together in about 10 seconds. Just finish your current thought. Okay, so as I am running this reaction over time, I am going to be slowly using up both chlorine and aluminum and making AlCl3. So as I go along, at some point I will have made 671 grams of AlCl3. At that point, I will have totally used up all 535 grams of chlorine that I have. I will totally run out of chlorine. So I can never make 673 grams because I have no more chlorine to use up. So once I've gotten to that point, I've totally run out of Cl2, and I will still have aluminum left over, because if aluminum was my limiting reactant, I could have made 1,000 grams of AlCl3. So what that means is that Cl2 is my limiting reactant and aluminum is in excess. So I'm just going to pause for a little bit and see if anyone has questions on this. The intro chemical engineering class, CBE 40, does a lot of this. So if this is fun for you, consider switching into CBE. This is my sales pitch. Shameless plug. Definitely a shameless plug for becoming a chemical engineer. Okay, I'm gonna have you do, so basically what I'm trying to do is I have some amount of chlorine and some amount of aluminum. And I wanna know, as I'm running this reaction, which one is going to run out first. So the best way for me to figure that out is, let's assume that Cl2 is my limiting reactant and I don't have to worry about aluminum. In theory, how much AlCl3 could I make? A couple slides ago, I converted to moles, I used my stoichiometric ratios, and then I converted back to grams, and I had figured out that I could make 671 grams of AlCl3 if Cl2 was limiting. Now let's pretend that aluminum is my limiting reactant. I'm not going to worry about chlorine. If I'm going to use up all of my aluminum, how many grams of AlCl3 can I make? So I convert 255 grams of aluminum to moles. I use my stoichiometric coefficients to figure out how many moles of AlCl3 I can make, and then I convert that back to grams. And I found out that by the time I've used up all of my aluminum, I will have made 1,260 grams of AlCl3. So that's the hard part. Those two steps involve a lot of math. You have to convert from mass to moles, use your stoichiometric ratios, and then convert back to mass. And then now that I have that information, I can just think conceptually about what's going to happen over time. So as time is passing, I'm using up Cl2, I'm using up aluminum, and I'm making more and more AlCl3. I'm going to make 671 grams of AlCl3 before I've made 1,260, right? So at the point over time that I've made 671 grams of AlCl3, I've totally used up all of my chlorine. Now I can't make any more AlCl3 because I'm out of chlorine. So chlorine is my limiting reactant. Basically because that amount of product that I could make is smaller. So that means that Cl2 is my limiting reactant. At the point that I've made up 671 grams of product, I'm out of Cl2 and I still have aluminum left over. So aluminum is in excess. And to give you a little more practice on that, have one more problem for you to discuss in your groups. So I have this reaction that's 3A plus 2B goes to C. So just as a reminder, A, B, and C are molecules of some kind. I haven't told you what atoms they're made of or what kind of bonds there are. You don't need to worry about that. You just need to trust that I have balanced this reaction. So the reaction is 3A plus 2B goes to C. And then, yeah, exactly, there's a question in the chat. Whichever one would make the least amount of product if I used all of it up is my limiting reactant. So yeah, that's exactly right. So go ahead and discuss this in your groups. I'll give you a few minutes and then we will come back together. Okay, does about 1 more minute seem like enough time? If not, let me know. Okay, I'll give you about 2 more minutes from now. So at about 11:31, we'll come back together. Okay, let's just take 10 seconds to finish your current sentence, and then we'll come back together. Okay, so for this problem, I have made your lives a little easier, or at least that was my intention, by giving you everything already in units of moles. So you didn't have to do any moles to mass conversion, you just needed to know how to use the stoichiometric coefficients. So I know that to use up my 10 moles of A, I'll make 1 mole of C for every 3 moles of A. So that means if I used up all 10 moles of A, I would be able to make 3.33 moles of C. If I used up all 8 moles of B, I'd be able to make 1 mole of C for every 2 moles of B. So that's that stoichiometric conversion factor there. And I would be able to make a total of 4 moles of C. So exactly like someone in the chat said, it's whatever one is less. So 3.33 is less than 4. So A is our limiting reactant. The way that you can think about that and remember it is that in order to make 4 moles of C, I had to have made 3.33 moles of C at some point, right? That's just how time works. And so I can't ever get to 4 moles of C because I'll run out of A at the point that I've made 3.3. So that means I'm going to run out of A first before I run out of B. So just putting what I just said into text, once I've made 3.33 moles of C, I'm totally out of A, which means that A is limiting. And then the second question that I put on here is if I had given you these amounts in grams, what would you do? You would need to convert to moles. So again, those stoichiometric coefficients only work in units of moles. And you would need the molar mass. So if I had told you that A is CO2 and B is H2O, you should be able to find that molar mass. But in this case, where A and B and C are made up molecules, I would need to tell you A has a molar mass of 20 grams per mole or whatever. So anytime you have amounts in grams and you want to use stoichiometric coefficients, you need to convert to moles using molar mass. Okay, so we have one more concept to go over today that builds on this. So if there are any last questions on limiting reactants, now is the time. Okay, so the last topic I want to talk about today is what's called yield. So my theoretical yield is how much C, or product more broadly, could I make if I used up all of my limiting reactant. So basically that's saying the very best that I can ever do as I'm running my reaction is using up all of my limiting reactant. Once I've done that, I can't make any more product. So theoretical yield is, given the amount of reactants that you have, what is the most that you could possibly make? And the most that you could possibly make happens when you use up all of your limiting reactant. So if I have this same reaction, 2A plus B goes to C, I have my 5 moles of A and 2 moles of B. I want to know what my theoretical yield of C is. So this is the same reaction that I showed you a couple slides ago in defining what a limiting reactant is. So I found that B is my limiting reactant. So just as a reminder, if I use up 2 moles of B, I can make 2 moles of C, whereas if I used up 5 moles of A, I could make 5/2, which is 2.5 moles of C. So B is going to run out first. So B is my limiting reactant. If I used up all of my B, which is 2 moles, I would be able to make 2 moles of C. So my theoretical yield is 2 moles of C. Now I tell you that how much I actually ended up making. So my actual yield is, maybe I used up all of my limiting reactant, but maybe, I am not able to use up all of it because my reaction is inefficient in some way. So I tell you that I ran an experiment in lab running this reaction, and the most that I was actually able to make is I made 1.5 moles of C. So the actual yield is pretty easy because it has to be given to you. Or measured in some way. You can't just look at a reaction and know what the actual yield will be. So that would be given to you in a problem. And then my percentage yield is just actual over theoretical, which is a fraction, and so we multiply it by 100 to get a percent. So this is basically how close did I get to my theoretical yield. So if I was in practice able to use up all of my limiting reactant, then my actual yield would be the same as my theoretical yield. My yield would be 2 moles. So then I would have 2/2, which is 1 times 100. I would have 100% yield, which is practically impossible. So that's the best we could do. So in this case, my actual is 1.5, my theoretical is 2, I multiply that by 100 and I get a 75% yield. So just as practice, if I have 2 aluminum plus 3 Cl2 to 2 AlCl3, so that's the practice problem that we've been kind of working with all day. What I had found before, so the problem statement is if I have 535 grams of chlorine and 255 grams of aluminum, which is the numbers that we had before, I'm telling you that actually in my experiment I was able to make 300 grams of AlCl3, and I want to know my percentage yield. So I want you to discuss this in groups for a couple minutes, and just to remind you all of the things that we decided before. So none of this that I just popped up is new information. This is what you solved for on previous slides. So I had found out that if I have 535 grams of chlorine, I can make 671 grams of AlCl3. If I have 255 grams of aluminum, I could make 1,260 grams of AlCl3. That 671 is less, so that means that Cl2 is my limiting reactant and Al is in excess. So I'm just like letting you skip all that math because we already did it on previous slides, but that problem statement, that 535 and 255 and 300, that is all the information you need, and you can use that information to solve for what I've found below. So given that, what I want you to do in your groups is figure out what the percentage yield is. I'll give you just a couple minutes. And as always, put questions in the chat. Okay, so let's just take like 20, 30 more seconds to discuss. Okay, so my theoretical yield is going to be 671 grams. So that is, regardless of how much I actually ended up making, the most that I ever could have made is 671 grams. After that, I run out of chlorine and I can't go any higher. So my theoretical maximum possible yield is 671 grams. What I told you in the problem statement is that when I actually run this experiment, I had an actual yield of 300 grams of AlCl3. So to get my percentage yield, I just take 300 divided by 671, and then I just multiply that by 100 to get a percent, and I end up with a percentage yield of 44.7%. Okay, so that is all we have for today. I'm going to give like 30 seconds or whatever to put questions in the chat, and then I will end the stream, and Katie and I will be in the Zoom room for any additional questions. Okay, I'm gonna end the stream, and then yeah, please stick around after in the Zoom room if you have any more questions about anything, not just this.